Server virtualization. In this section, we look into the details of server virtualization. As part of this section, we will define server virtualization. Then we will look at the various components of server virtualization, namely CPU virtualization, memory virtualization, and I/O virtualization. Then we'll look at several server virtualization solutions. The reason it's important for us to understand this is because different cloud vendors use different solutions. In fact, within the same cloud vendor, they may have one or two different solutions implemented as the technology changes. And then finally, we'll look at physical infrastructure versus the virtual infrastructure that's made possible because of virtualization. So what is server virtualization? Server virtualization is basically taking a single machine and chopping into pieces so that you can have multiple virtual machines within that single physical machine. There are three components that make up server virtualization, and that's CPU virtualization, memory virtualization, and I/O virtualization. Because if you really think about it, when you take a server, a physical server, if you look at it, there is the CPU, there is the memory, and there's the I/O devices. These are the resources that need to be shared across the various virtual machines that may be running their own operating systems. As you can see, the CPU is being shared across or time sliced across the different VMs. The memory has to be shared across the different VMs, and the I/O communication that's happening to the NIC card, which is the network interface card, and the hard drive also has to be time sliced. So server virtualization is all about sharing CPU, memory, and I/O resources across the different virtual machines. What drove server virtualization? There are actually two IT trends that drove the need for server virtualization. The first is the explosive growth of Microsoft Windows on servers in data centers. As the 1990s approached, when we started coming out of the 1980s PC model and the desktop model, more and more companies started having their own email servers, their own web servers, app servers, and file servers. So many data centers started getting filled with these different servers. And over time, with the constant increasing capabilities of the corporate servers due to Moore's law, which basically says that every 18 months the capacity of the system doubles, many corporations ended up having servers that have a lot of capacity, a lot of RAM, a lot of storage, a fast I/O device, network card, fast network, and fast CPUs. So what do you do with it? Well, could we share them? Could we use virtualization to kind of consolidate all these different servers? And that's what really drove server virtualization. So let's look at CPU virtualization. What is CPU virtualization? The basic idea behind CPU virtualization is, let's go ahead and take our physical server, which has got CPUs, multiple cores, and let's chop it into pieces so that I can give each VM, which is running its own operating system, a slice of the CPU, or maybe a portion of that particular CPU, or maybe just give the code to the CPU. Typically, you want to give a slice of the CPU. There is this concept called the physical CPU versus the virtual CPU. So what we want to do is virtualize the CPU. That's really what CPU virtualization is all about. Now, in order to understand this, we need to understand what is called the rings of the operating system. So let's look at the rings of the operating system. It so happens that you have hardware, and then you have operating system that's running on the hardware, but then it doesn't really just run as just a process. It so happens that in the hardware and the operating system, there are these rings. Ring 0 is the most important ring. It's also called the most privileged ring. This is where all the kernel logic is executed. Then there is ring 1, which is where the device drivers are executed, and ring 2 is also device drivers. And then ring 3 is where the applications run. So ring 0 is the most privileged, where the kernel code runs for the operating system, and ring 3 is the least privileged. This is where your applications run. This is how typically the operating system architecture is done. Now, why do I want to talk about this? Because in a traditional hardware and OS model, you have the hardware at the bottom right here, and then you have the 4 rings. ring 0, ring 1, ring 2, and ring 3. The operating system kernel runs on ring 0, and then the applications run on ring 3. So whenever the applications are running in user mode versus the kernel mode, they would just operate on the user mode, use the CPU, and do the processing. But whenever an application wants to run in kernel mode, for example, wants to do I/O or wants to access direct memory, it needs to come into what is called the kernel mode. At that point, the kernel takes over. Now, many of the x86 operating systems are designed to run directly on bare metal hardware like this. Well, they assume that they have complete access to all the system resources. But what we really want to do is we want to have something called VMM, which is the Virtual Machine Manager, which abstracts the hardware or the system resources, especially in this particular case, the CPU. How do you do this? Well, there are different solutions that are out there in the marketplace for CPU virtualization. They are invented by different companies. There is full virtualization. There is OS-assisted virtualization, which is also called para-virtualization. And there is also hardware-assisted virtualization. So these are the three different options that we have. And different hypervisors, which is the modern term for VMM, which is Virtual Machine Manager or Virtual Machine Monitor. The hypervisor is the one that is going to implement one of these different virtualization options. And the reason I want to talk about this right now is because when we start getting into cloud computing, you will see that they will mention to you that they are using this kind of a hypervisor. Like, for example, they might say they're using para-virtualization or full virtualization or hardware-assisted virtualization. So it's something to note and understand, because sometimes you may have to reboot a machine because they've changed the hypervisor model under the hood. Okay, so let's look at full virtualization. In full virtualization, the VMM, which is the Virtual Machine Manager, actually runs on ring 0. And then the guest operating system is going to run on ring 1. So as you can see, the guest operating system is running on ring 1. In this model, the guest operating system does not have to be modified. It just runs the way it is, except it runs on ring 1. And notice the applications are going to run on ring 3, which is perfectly fine. Well, we have the hardware over here. Now, what happens when the operating system is running and the user applications want to run on the kernel mode? Well, in that case, basically, those instructions are trapped and passed on to the Virtual Machine Manager, which then translates it and runs it on the hardware. So the point I'm making here is that the guest OS faults on some instructions because those instructions cannot run on ring 1. Notice the guest operating system is running on ring 1 and it has not been modified. It has not been modified. And so it can lead to faults which gets caught by the VMM, which runs in the hardware. So that's full virtualization. The second model is what we call the OS-assisted or para-virtualization model. In this model, we have the hardware, and then we have a virtualization layer on top of the hardware. So there's a little bit of support that's coming from the hardware in this particular case, and that's where the virtualization layer software is running. In this model, Machine Manager is running on the special layer. The guest operating system runs on ring 0. The guest operating system, however, has been modified to run on ring 0. Remember, the guest operating system likes to directly access the hardware for some of the x86 operating systems. Here, they change all those instructions and they make what is called hypercalls. So those hypercalls will come to the virtualization layer, which will make the calls to the hardware. And so that's how the OS-assisted or para-virtualization works. The most important thing to remember here is that the guest operating system is actually modified in this model. The next model is called the hardware-assisted virtualization. In this model, the hardware vendors are providing some capabilities in terms of virtualization. You have the hardware, and then you have the Virtual Machine Manager, which is the hypervisor software that's running over there with root mode privileges. And then you have your normal 4 levels, ring 0 through ring 3. Your operating system is going to run on ring 0, which is the guest operating system, and it doesn't have to be modified. And then the user applications are also running in ring 3. The only difference here is that in this model, the guest operating system is going to make some calls which are automatically trapped by the hardware and is passed to the VMM. So the VMM doesn't have to do anything other than just executing it in the hardware. The guest operating system does not have to be changed because the guest operating system will try to execute that logic which will be trapped by the hardware and sent to the VMM in this particular model. So that's the third model. Now let's look at the physical and virtualized host memory usage. We talked about CPU virtualization. Now let's talk about memory virtualization. Once again, we have a piece of hardware. The hardware has memory, and the operating system and the application likes to use that memory. But with virtualization, we have our hardware, we have our memory, but then we also have the VMM, which is the virtual machine manager layer, which is going to chop up our memory and give it to the various virtual machines. In this case, it's giving 1 gigabyte to one virtual machine, 2 gigabyte to the second virtual machine, and 8 gigabytes to the third virtual machine. Let's see how that works. Basically, in this model, what happens is every virtual machine, in this case I have VM1, which is virtual machine 1, and VM2, virtual machine 2, has its own process. In this case, virtual machine 1 is running two processes, process 1 and process 2. Virtual machine 2 is also running two processes, process 1 and process 2, and it requires its memory. So each process is having its memory. All this is memory that's needed by process 1 in virtual machine 1, and this is the memory that's required by process 2 in virtual machine 1. This is the memory that's required by process 1 in virtual machine 2, and this is the memory that's required by process 2 in virtual machine 2. But every virtual machine has something called virtual machine memory. That's this one right here. Now I'm using this term called VMM. Pardon me, it's not virtual machine manager or virtual machine monitor as defined by the two guys from the 1960s. This is virtual machine memory. This is VMM, which is the virtual machine memory, which is the memory that is being allocated for the virtual machine by the hypervisor. And this is the physical memory. So what you're seeing in yellow here is the physical memory, which has been chopped and has been given to the virtual machine memory. And every virtual machine has been given different amounts of memory, which is being given to the various processes within the virtual machine. So there are three layers of interactions that's going on. There is the process memory, which maps to the virtual machine memory, which maps to the physical memory. Now in this model, something very interesting that can take place is overcommitment, also called ballooning. Now you may have only 16 gigabytes of RAM. Now you may say, I want to give 4 gigabytes to this VM and 8 gigabytes to this VM, but it's possible that this VM is really using 6 gigabytes and the other 2 gigabytes are not being utilized. And because the hypervisor is sitting in between, interpositioning every call, the hypervisor can actually come in and do what is called memory overcommitment. It can say to this virtual machine, oh, I can give you 10 gigabytes of RAM. And it'll tell to this virtual machine, I can also give you 10 gigabytes of RAM. But there's only 16 gigabytes of RAM that's physically available. That's because the hypervisor says, well, I'll give you 10 gigabytes of RAM, but I'm not really going to give it to you. I'm just going to make you feel like it's there, because I know for a fact that everybody is not utilizing all the memory at all the times. And so in this particular case, it fakes it out. And when one really needs it at that time, it gives the real memory. So it's almost like faking the memory. And this is very common in virtualization. It's what is called overcommitment. Similar thing can also be done in CPUs. They can say that I'm giving you 8 cores, but they're really giving you 4 cores. So there are all these games that can be played. And you have to be very careful with virtualization, because you may think that you have a lot more computational capacity or a lot more memory, and sometimes you could get into trouble. There is also I/O virtualization. I/O virtualization is really all the other I/O devices like your NIC cards, and you can have multiple NIC cards, you can have multiple sound cards and video cards, SCSI cards, this mouse, USB drive, all those are I/O devices, and they also have to be hypervised, or they also have to be virtualized. In this particular case, what I'm showing you is that the guest operating system simply creates a virtual device driver, and of course there is the physical machine with the physical device, for which there is the real device driver that is in the VMM layer. This blue layer over here is the virtual machine manager layer, and it does all the emulation of the real device to the guest operating system. So the virtual machine monitor virtualizes the I/O peripherals in the case of I/O virtualization. Here's I/O virtualization a little bit more detail. We have the hardware. There might be multiple I/O devices. For each I/O device, there is a hardware device driver which the hypervisor or the virtual machine manager cares about. The virtual machine manager is abstracting the devices, and every guest operating system is simply having its own virtual device driver which is communicating with the virtual machine monitor. Because the virtual machine monitor or the virtual machine manager can interposition itself, it can do things like compression, bandwidth control, overshadowing, multiplexing, scheduling, copy on write. Different kinds of operating system technologies and virtualization technologies can be used by the VMM layer. That's I/O virtualization. Now let's look at physical infrastructure. The physical infrastructure or the data center in the old model used to be, you would have a network in a data center, you would have your storage devices, your network devices like routers and switches, and then you would have other fiber storage. All these things should be connected, and what you're seeing here are physical servers. They're all physical servers, each having its own operating system. That's the old model. We have lots of servers in this model. But now with the virtualization model, what we can do is we can have one physical server having multiple VMs and operating systems in it. So you're really getting into a modern virtualized data center where you are having more VMs or more servers within a data center. And you can see now, if we can somehow bring some kind of automation to this, how cloud starts coming into play, how you can dynamically launch virtual machines, use them, and then destroy them. And that's really the idea behind virtualization, especially server virtualization. Why server virtualization works? The primary reason server virtualization works is because if you actually look at utilization, let's say you have one server and you have Joe, he's using the server, and his usage of the server looks like this. You have, that's Joe right there, that's Joe's usage right there. And let's say Jane also is using the server. Jane utilizes the server this way. This is Jane's utilization of the server in terms of CPU, memory, and disk. And then we have Robert. Robert is utilizing the server this way. And the point I'm trying to make is, if you actually average out everybody's utilization, it's probably somewhere over here, which means you can actually have one physical server, but that one physical server can handle 3 VMs for 3 different users, or 3 VMs for the same user. It doesn't really matter. But the point I'm trying to make is, because of the law of averages, server virtualization works really well. In summary, server virtualization is the ability to run multiple virtual machines in a single physical server. There are several components that make up server virtualization, and they are CPU virtualization, memory virtualization, and I/O virtualization. We looked at all 3 of them. CPU virtualization is breaking the CPU across the different virtual machines, and we learned that there are several kinds of CPU virtualization. There is full, para, and hardware-assisted CPU virtualization. different cloud providers, different hypervisors use different virtualization technologies. There is also memory virtualization, which is the application memory being mapped to virtual machine memory, which is mapped to physical memory, which leads to what is called overcommitment or ballooning of memory. There is also I/O virtualization, which is virtualizing devices. Hardware may have several devices, USB device, it may have sound cards, it may have network cards. All those things get virtualized by the virtual machine manager or the virtual machine monitor, and then eventually passed on to the actual virtual machines. Server virtualization basically allows us to move into a virtualized infrastructure within a data center, and so that helps us in doing what we call server consolidation.